Hey guys, so in this video we are going to cover the low-level design for the Tetris game. Let's first try to understand what is this game basically. So if you see in this picture, you can see that there are multiple blocks, colored blocks, having some different shapes. So they are falling from the top, and we need to arrange them in the given this bottom space. The that score and the game is more about basically storing more and more blocks in the given space. So you can rotate these shapes, you can move these shapes to the left, right, and all that thing, and trying to make sure that we can accommodate the more and more blocks in the given space. So yeah. So let's see what we are looking to achieve in this design. So the feature required is we need to have the board creation and the management. When we say board, it's more about this board which you can see. Okay. Then falling Tetris blocks. Basically, these blocks which are falling from the top to bottom. Then the next is rotation and the movement of the Tetris. As I said, these Tetris block can be either moved to the left or either can be moved to the right, or they can be even rotated. Basically, like rotated by 90 degrees, something like that. So this is what we meant. Line completion and scoring. So the line completion is more about, if you see this entire picture, you can see these gray blocks. So the line completion means if you are fitting any block above that particular line, that means you are done. The game is over. So for this, you can see there's a square here. For example, you can see this one. If you see this one, yeah, so this is the line of completion for this game. So if any block is going outside this boundary, then basically the game is over. So that is what we meant by this line completion and scoring. Of course, like how much you have scored in that particular game. Game over condition. And then we have the rendering of the board. So whenever, if you have already designed the game before, you must know that whenever you are making any change in the whenever a change is happening in the game, you more probably re-render the entire screen basically. For example, if even if this block is this green, or sorry, this yellow block is moving from one place to another place, then you need to then you re-render the entire screen, or there can be other optimization also. Maybe you just need to re-render that position of that yellow block, but that is what we are talking about here. Handling the players input. So again, basically players have these inputs which they can provide by the tool, whatever remote and whatever they have, move left, round, or rotate. They only have these things. Okay, so this is what we need to design for this Tetris game. Okay, so let's see what patterns we are actually using. So one thing is factory pattern. Again, you must, I mean, this is one of the like more intuitive one. We are using this factory pattern to create these blocks which we are having. So if you see this yellow block, red block, green block, blue block. So to create all these kinds of shapes, we are using this factory pattern. So we can just call this pattern and get the type of the shape which we are looking for, or the lattice block which we are looking for. Okay. So strategy pattern is more about the algorithms, how we are going to rotate all these shapes. Okay, so for example, a rotation can be done in multiple ways. Like for if you are given a matrix and there is a block which you have placed, then you can rotate that particular block. There are in some multiple ways. So we are using this the strategy pattern just for that rotating part. So if you see, some shape can rotate 90 degree increment, others can have complex rotation. Okay, so for now we can have only 90 degree increments of the rotation, but in future we can have more kind of uh, a change of the degrees. Like it can be anything 0, 1, 2, 3, 4. So it can be better handled by the strategy pattern. The next thing is observer pattern. Again, whenever there is an update on the board, you most likely be going to be update the scores, levels, and you also need to kind of update the blocks also. For example, when a user gave the command of left, okay, and you are done with that command, you have processed it, so you need to re-render the board also. Basically, you need to inform the board that that the board needs to be re-rendered, and we need to show the new screen to the user. So that is what we are using, and again it goes to the score managers also. Singleton pattern. Again, everything we are holding under this game board class. Basically, we are using the singleton pattern to make sure that we are only having a one instance of the game board for now. Command pattern again, like very intuitive. Since we are having multiple command, moving left, moving right, rotating, we are using the command pattern to handle all those movements. So we can encapsulate everything, whatever is related to the command specifically. Template method pattern. So the reason we are using this template method pattern, I will tell you while we actually start going through the actual code. But just to read it out, implemented the base. So basically, we have created a base class with this name Tetromino, and that class is going to be implemented by some other block. So because the thing is, every block can have different kind of operations like falling, rotating, moving for that part. You will get to know. I mean, this does not look good for now, but we will get to that part once we start looking more into the code, basically. As it is mentioned here, we are basically each shape is little bit rotation specific. Okay, so if you will rotate this square, you know the rotation for the square is not going to be same as the rotation of this green, sorry, this yellow block, which you can see at the top. So that's why we are having this this class. But again, we will cover that in the upcoming part. The algorithm which we are covering here is, as you can see, again the rotation of all the types of the Tatanino we have. Line completion, how we are going to find out whether the line is getting completed. Basically, that all the rows are filled, which we have as we have just discussed, that when how we will be deciding that the game is done. Okay, so that is what it is here. Collision detection, it's more about when you are putting block onto another block, so there is always a collision. So so that part of the algorithm is more about detecting if a block movement is can if a block even can be rotated or not. For example, if you see this top block, which is this one, green one, this one, so this is fine now. You can rotate it. But if you rotate it near to this green one, definitely rotation will not be allowed in that case, because it will be um, collide with these red blocks. Okay, so if we are having multiple algorithms just for the collision detection to make sure whether the move which is provided by the user is even valid or not. Okay, it may look valid in some condition, it may not be valid in another condition. Okay, now let's move to the code. Okay, it's getting loaded. Now we'll see how the code is actually working. There is one thing which is missing in this code actually. It's um, about the cleaning. For example, when this block is moving from one location to another location, I missed that kind of small code from this given code, so that I will basically update the code. But I will explain that part also, that how it is actually going to work, or maybe you guys can by yourself try it out. Okay, so let's see this one. Okay, so if you see, we have this. Right. Yeah, so we have this factory pattern which we are using to create a multiple types of the shapes. Okay. Again, this is our command pattern which we are using. So we have this I command interface which is implemented by the move left command, move right command. Okay, and this touching in also. You will get to see like how this entire architecture is looking like. Right now, it may look very complex to you, but no, it's not like actually that way. Okay. So here, if you see this Tetromino class is implemented by different classes. One is this T block, then I, then L. These all are shapes basically. As we have discussed, different block can have different way of rotation. The rotation logic for one shape may not work with the another one. So that's why we are implementing this Tetromino class for all the shapes. One goes for this L tetromino, another one is this I, then L. So all these three are shapes T, I, and L. Okay. So, and that is what we are doing. So these three class is implementing this Tetrimino class. This I rotation is why this I rotation is shown connected to the Tetrimony, because this Tetrimino class is actually using this I rotation. I rotation strategy is not implementing this Tetrimony at all. As you can see, this association is written here. Okay, so again, this I rotation strategy is a interface which we have created, and then again we are creating this standard rotation strategy. So we are basically using the strategy pattern here to have multiple kind of strategy for rotations. Clear? Okay, again, this game board which we have discussed, even in the previous video, I've discussed that whenever you see this self association, it's more probably likely going to be a singleton pattern which we are using there. Okay, now let's actually see the code. Okay, let's start with a very basic, let's say, command. So here we are just having a simple interface which we have created to have multiple types of command. Okay, one which we are having is this move left command. Another which we are having is this one, which is move right command. Okay, so what we are doing in this move right command, if you see, there is a function called execute function which needs to be implemented by this class. This is actually calling this function called move right. Why we are not having the logic of this move command within this one? If you see, the actual movement logic is residing into another class. It is not actually here. So if you see, there is no logic related to the movement here. As I said, movement can be different um, for the different shapes. That's why we are having this basically. Mostly, I think we could have even had the one, we could have even moved it here, but at least I will just explain what is written in the current code. We can think more about the optimization later on. Okay. So if you see here, we do not have any logic for the move right command. It is actually written in any other board. Then why this move command is actually required? It is just to encapsulate whatever is required to complete that action. So tomorrow, if you want to do something else also, when someone is triggering the move right command, so you can just add it here in the line number 14. So that it works out that way. Similarly, you will find out in the left command itself, in the left command also, the movement of the tetrimony is not actually done by this class. The code is not residing in this class. It is actually again residing in this tetrimony, which is actually an interface which is implemented by the multiple classes as we have discussed, L, T, and I. And the movement, they are actually holding the logic how they are going to move that block. Okay, so that is what we are done with. Now let's go with the tetrimony factory. So as you can see here, as I told you, we are using this factory pattern to create multiple different shapes of the tetramino. As you can see, L, T, for now we are only covering these three shapes, but in the end of the blog we have discussed about adding more shapes also. Okay. So based on the type which you want, it will create a tetramino shape. It can be L, T, I. For now we are only working on this one. Okay. Now let's go to this class. So this is the abstract class which we have created. This actually represent this shape. This shape, for example, this yellow shape, this pink shape. So this yellow one is L, this pink one is T, and I actually, yeah. So you can see this one is I. Okay. So this entire data is held in this tetrimino class, which will be implemented by the L, then I, and then T basically for a specific shape. So everything related to this one, specifically this one, let's say this one. It's like, hey, what is the current location of this tetrimony? Okay, what is the type of this tetrimony? Okay, what is the shape of this tetrimony? Everything is going to be resides in the class which is implementing this tetrimony abstract class. For example, as you can see, there is a shape. Okay, it is, what do we mean by shape here? How we are actually representing the shape. So if you see this one, the way to represent this shape in this 2D matrix would be, the yellow color would be 0, 0, 0, 0, and then 1, 1. So what we can say is, if we take this yellow one and if I show you this yellow one, how we can represent this in matrix? It will be like this: 1, comma 1, comma 1. Okay, sorry, and then 1, comma 0, comma 0. That is how we are representing the shape of this tetrimony in this class, in this shape variable. So it is not holding the location. This is only holding the how the shape look like. What is the shape actually? So if you see just one you follow, you will get that this is L shape. I'm just telling you by the example. Okay, for let's say for if you want to represent T here, okay, the way would be something like this. Okay, this is how you can we are representing the class under this thing. Next is this protected XY coordinates. Again, as I said, this XY coordinate is actually holding the location of this tetrimony. Okay, I will come to that place, like how it is actually working out, because so don't worry about that. Another one, as I said previously, also different shape can have a different rotation. The way they rotate, the strategies to do the rotation can be different because the shapes are different. Okay, so that's why we are having that thing specific to the class. L1 can have different, T can have different, F maybe any other shape can have different, or maybe we can have even a one single class which can handle all the rotation. This is again nothing other than the constructor. This is rotate function. This is move left function. Okay. I think we can move this move left function in the game, sorry, in the command pattern, but I will just explain what you are written currently. Okay. So you just provide the board here and it will first check, but definitely. So whenever you are making any move, you need to must make sure that it's not colliding anything. Basically, it's a valid move or not. That is what we are trying to check. If it is valid move, then it's allowed, basically. Okay, it's fine. Okay, there is one more thing I will tell you. Here we are missing one thing, which is placing this new, I would say, placing it to new place. Okay, and cleaning the previous. That is that I was saying that hey, these two parts were missing in this code. I forgot it. Okay, so whenever we are moving left or whenever we are trying to do that, we first are cleaning the previous state of that shape. For example, where it is previously colliding, sorry, where it is previously there. So first we clear the position of this block from the board, and then we check whether the new state of that block is colliding in the board or not. If it is not colliding, then we place it basically. That is what we do. Similarly goes for the move right. Similarly goes for this move down. Okay. Other things are just nothing get set, something like that. Nothing negative. Okay. Let's come to T1. So if you see here, we have initialized this T by providing this shape itself. So we first provided the standard, sorry, rotation strategy. And this is how, see, as I discussed, this is how you can represent the T. This is inverse T, you can say, but you can do it in any way, that will work. So there is no issue with that. And this is the initial location of that, this T-shaped Tetris block. This is the initial location of that. Okay. Goes with the eye. So as you can see, this is how we are representing the eye. Straight line, nothing else. Again, we are initializing it this way, basically. For the L, as we have discussed, this can be other way also, like the way we have discussed. Everything is fine because we can always do the rotation and movement. So that is again fine. Now let's first come to like how we are actually placing it into the board. Okay. Let's come to the game board now. So this is the is collision function which I was talking about. That this is how we are checking whether the blocks are whether the new move of the block is getting collided with the existing block or not. This is the place command which I was saying. Okay, this is what we need to use there. Let me show you. So here basically here we need to do something like this. If board place this. Okay, so this is what we need to do. So as you can see here, you just need to provide the this tetrimony And as I said, every data related to the position and shape is already there. So they just place it. They don't need to specifically, we don't need a specific method for different types of shape. Everything is just handled by the one function. Okay. So we just provide this here basically. This is how we actually do it. Okay. So we need to place this. Sorry. We are going to place this here basically. Board dot place this one. This is what were missing. And again, we have something like this. Okay. We will have something like this basically. It's not there. I will update the class again. But this is not such a big piece. What you normally do is wherever you have set this coordinates, you just reverse the transaction, make all the coordinates, make all the values to at zero. Of those 111 to 0, nothing else, nothing else. It's just the cleaning is that simple. Now let's come to game board. Now let's first talk about how they are actually placing the trend. Okay. Now we'll explain you how the placement is actually working. Right. Wait. I'll have to show you. Let me create a matrix here. Let's say this is how the X and Y, the graph of the entire board looks like. So this is like an entire graph only, like a matrix you can say. Okay, so we have something like this, let's say. Okay, then we have, wait, I'll just paste it out. Okay, so we have something like there. Now, now we have a shape of, let's say, what shape you will like to we will use is, let's say we are using t here, simple t, z, sorry, 1 comma 1 comma 1. Okay, then we are having 0 comma 1 comma 0. Okay, this is what is we can say t shape, correct? Now we are having the location, so x is, let's say, 3, sorry, 4, let's say, and y is equivalent to 1. So the way it start is we start iterating to this entire shape location, this one, let's say this is 0 comma 0. So we say this value na, will go to 4 comma 1. Another value, the next value will go to 4 comma 2 basically. The next value will go to this one will go to 4 comma 3. So that is how we are actually placing the entire tetromino into this and into this board. So if you see here, we are iterating over the shape values, and then whenever we are placing, sorry, this is its collision here. Whenever we are placing, we are first checking whether it is not equivalent to 0, because there is no point of placing 0 again. We are okay. This is what we are doing. If you see x comma y plus j I. That is how the placement on the board is actually done for a tetromino. This will work on any shape. You can try by yourself. LT, 0, whatever. You can introduce any shape. This will work for everyone. This is how we are actually placing the tetromino. Again, the same way we are checking the shape. How we are checking the shape? We are saying that, hey, we are going to place the block here, and if any of the particular element is already holded by someone else, so that means there is a collision, and we are always returning true. That's why I was saying we need to. That's why we were. If you go here, that's why I was saying that we need to clean the previous tetromino. We need to clean the previous location of that shape. That's how the entire collision is actually working. Let's go to the game board again. Okay, so I think we have covered the more important part about how we are placing the shapes into the board. Is collision, as I mentioned, place. Check line completion. Again, we are checking whether the block which we have filled have not gone beyond the things or not. Okay, so you can just check it out how it is actually working. It's not going to be a big deal. Initially, what we are saying is, hey, we are considering that the line is full. Basically, we are done with the entire board. That's how we assume. Then we find out if even if there is any space left. If there is any space left, we say it's not a full line yet, basically. Okay. Clear line, render board. As I mentioned, this is just to render the board. If you see the output, this output is about rendering the board. After every movement, we just re-render the board to show the updates which is made by the user, basically. Okay. I think I just need to showcase one more thing. Wait. Yeah. Let me see if you are missing anything. So, so this is I have just created a basic class for you, so just to see how we can basically use all these classes and to get the implementation done. Okay. Again, we are having this game board where all the location we are holding the state of the current game. Okay. We are again getting the instance, creating some shapes here, and then this is how we are actually our game is done. The normal way. Normally, what you do is you have a true here, and the key game keep running on and on until unless you hit a game over or some interruption by the key. Okay, so that is how it's normally done. But I can do it. Otherwise, the compiler will go into the infinite loop. So that's why we have not done it. Uh, I'm just trying to see if we have anything to cover yet. Okay. Um, Tetris game. I just covered it up. Okay, just one more clarification about this check line. So if you see this entire function again, so what this check line is actually doing, it is going through the entire matrix. It is basically going through the entire matrix, and if it sees if there is even a single cell which is not set to true, basically which is empty. For example, here you can see this space is empty. That means it's not a full line. What do we mean by full line? What do we mean by check line completion? It's Sorry, I think I messed up in beginning. Checking line completion means checking out whether the entire board have got filled or not. When I say got filled, every single space should be filled. Even if there is one single space left, that means full line completion is not done. Okay, this is what we are checking here basically. So if user has kind of used all the spaces very well, we are incrementing the score by 100 plus, or you can even say that hey, the user got win. Because if the user have occupied all the cells, that is the actual motive of this entire game, making sure we are utilizing every cell, every empty cell of the given board, and we are filling it somehow. So that is what we are checking here basically. Okay. Um, what about this clear line? So what this clear line actually do is basically it cleans the entire line of that particular row basically. So, for example, in the Candy Crush, it happens. Example, if there is a huge, basically, if there are multiple same kind of blocks in the row and they are continuous, there is no space left in between. So basically, we clear that line and we increase the score by 100. Same thing which we are doing here. So if you see, if it is full line, that means all the that particular entire row has got filled. If you see, we are running it on the heights. Okay, full line, we are considering that hey, there is no full line, everything is full line right now. We are considering that's how we are the logic of the calculation is. If we found even a single space, we mark it false and then we don't do anything. But if we found out that entire line is filled, we increase the score by 100 and we clear that line basically. Okay, so that is what we actually do. And Yeah, I think that should be good, fine enough. There is one more thing we are doing. So same thing which we do in Candy Crush, if you guys remember. If let's say if I am clearing this bottom row, then all the rows which are above that they will fall under the simple basic rule, simple basic thing. So definitely we need to move all those rows also to the bottom, to the next, to the downside. Here we are doing that part. So if you see system array copy, it's what it is doing actually copying the entire row from the previous line to the next line, basically to the downside. Basically, that's what we are actually doing. And then we are setting that particular row to 0, which we have just cleared basically. Okay. um Basically the top one. Okay, so the very simple thing it happened in the Candy Crush, you remove the bottom layer, everything fall under down, and the at the top layer becomes 0 0, something like that. So that is what we are also doing here actually. I think I've covered everything. Render board is done, clear line is done, checkline completion is done, place tree, tetromino is done, is collation is done, game board. Okay, we can talk about the rotation strategy, but again, it's just more about kind of a DSA algo thing. I would say we are having the tetromino, which holds all the information about that, like the location, current location, the shape, and we are holding the board. Now we need to check um, uh, whether the collision is going to happen or not. And what we are doing for that is we f- uh, we are creating this new row, the rotated array, and then we are filling this entire 2D array with the new location of that shape. What we are doing is we are placing that shape with the rotated values in a new array, and then we are checking whether the collision is happening or not with this one. See, if you see. So this rotation strategy is not doing anything much. It is just placing that block in a rotating way. Okay. Now they basically match whether the rotation is allowed or not. Okay, let's go through this one also. I think this is more needs to be explained more. Standard one, we are having this one. Where we need to go. Okay, board is collision. We are providing the shape here and we are providing the XY. So what we are trying to check here is whether it is colliding with the board or not. And this is the board here basically. Let's go again there. So this n is the size of the shape. Basically, it can be whatever the shape size we are having. And here we get that one. We get the coordinate of x and y basically. And then we check whether this shape can be kept at x or y or not based on the given current board basically. So we are not doing anything different. Same thing which we were doing with the with that move left or right command. For the move left and right also we were using this is collision. For the for the rotation also we are doing the same thing. But the only difference is the rotation part. We are not just providing the shape as it is, which we used to do in move left or move right. If I show you here, for move left and move right, we are providing the shape as it is without any change. Because the movement is only left and right, so we do not need to change anything. Because when we do the rotation, if you see, the simple T will become the inverted T or something like that. So that require change in the coordinates of the shapes values. For example, here if I rotate this one, so the way it can look like is something like this: 1 comma 1 comma 1 and then 0 comma 0 comma 0. So what that rotation strategy is doing, it is converting this thing to this way, and then providing this new shape and checking whether, hey, can we even place this at that coordinate or not, and nothing else. If we find the collision, no, otherwise it's fine. Okay, I think that is what we are doing here. I think I have covered mostly everything. Let's go to the other part. Now, let's talk about this time and space complexity. So every movement which is left, down, or right, which we require checking the collision. So again, it will take on time, or you can say n into m time, if we are going with the n basically where it says row into column. But here n represents the number of cells in the tetrahedron. So you can say the size of the matrix itself, n into whatever you want to say. So it's more about the number of cells of the tetrahedron will be deciding the time complexity of the movement basically. Then the rotation. So the issue with the rotation is, in rotation we require transformation, as we have just recently discussed, that we need to do the transformation of the entire. We need to do the matrix transformation to represent it in a new shape, basically like rotated shape. So for that, as we have seen, we are using this. Uh, yeah, so we are kind of doing the n square basically. Okay, so it will take a big of n square. But here n is equivalent to the size of the shape basically. Okay. Every line completion check, again, as I said, it will require OW time per row, where W is the width of the. You can actually eventually see the number of cells in the entire matrix. So that is how we can see that. Now, what are the other optimization which can be done? So, if you see tetromino are created frequently, like for example, even in this picture, you can see there are multiple tetromino. So, don't you think every time creating a new tetromino can create a havoc for us? Like, I mean, basically, let's say you created hundreds of tetromino, and now during the line completion, few of them will be cut. Now, the garbage collectors definitely needs to clean that out. So it will be a huge cost if we are doing this frequent thing. So instead of doing that part, we can create an object pool to have these creation of the tetraminos instead of creating and deleting them in the way. So it can help us to reduce the overhead of the GC basically, which is the garbage collector. Other improvements, which is, what if the Tetris shapes are completely unpredictable, more complex? So right now we are having a specific shapes like LOT. It can be, why we can't have any shape? O, P, I mean like anything. Why we can have a custom shape? So that is what we need to change the system according to that, so that we can have the random shapes also. Again, we have covered it in our course. What if you have to run this? So, do you guys really think this will actually work on the Raspberry Pi or some other systems where there are limited resources? As we have just discussed, if we keep having starting, if we keep adding the tetramino or whatever T shapes, it will start having taking more and more space. And if we are having larger board, then again you can think of like how long, how high space it is going to take. So we need to work on optimizing that part. Will this same code will work on Raspberry Pi? No, it will not work. We definitely need to optimize it by a great margin. What if the system were offline? If the system is were offline, does the same thing will work, or is there need changes or optimization we need to do compare to the offline system, or if it is just a single system, like say kind of a software which you have installed into your system, which is not required to be connected to the online system? Does the system really work according to that? I don't think so. Again, because when we are having an online system, it's not just you who are going to use it, multiple people are going to use it. And if you're creating this tetromino with these bases that we have just discussed, it's going to be a havoc. The calculation is also, there is an issue. We are taking too much time for calculating the things. Again, we need to work on those strategies also. So all of those things are covered in our courses. It's already there in the form of blog in the course. Again, I will add the video also for the same. But it's in the for the blog, as we can see here, it's already there in the course. Okay, I think we have covered everything. Yeah, I think, yeah. So thank you guys. Just let me know if there is any issue or if there is any change you think we should make or if there is anything better which we can do. You guys can mention it in the comments section.